Hey, so welcome to the week 5 of the LabView class. In this week, we're going to talk about how to acquire data and communicate between a computer and a LabView when you have the actual instrument that is connected to your LabView. For example, if you have a pressure transducer, or if you have some pumps, or an oscilloscope, or all these kind of different things that you can have. So let's get started. There are two kinds of signals that you can send to the computer, the analog and the digital signals. Here you can see like how the analog signal looks like and how the digital signal looks like. So analog and digitals are the different forms of signals. Signals are used to carry information from one device to another. Analog signal is a continuous wave that keeps on changing over time period. Like if you have a voltage or current that you are getting from your instrument. Digital signal is discrete in nature. It means that it's like 0, 1, 0, 1. They are like discrete numbers. The fundamental difference between analog and digital signal is that analog signal is represented by the sine waves, whereas the digital signals is represented by square waves. So it can be either 0 or 1, 0 or 1. So just keep that in mind that we can have analog or digital signals. Okay, so in today's video, we're going to talk about RS-232 serial communication device. So before we get to that point, let's continue with the analog and digital signal. So for example, as I said, if you have a pressure transducer that you want to measure a pressure, your transducer have like cables. It can have 2 cables or 3 cables. And these cables are gonna provide you, or are gonna give you some voltage or some current signals. And this is called an analog signal. But sometimes you have an instrument that doesn't have this kind of cable, like the voltage or the current, and your instrument has this kind of pins. This is a digital signal. That means that it's sending 0 or 1, like beats at a time. We call this like this kind of like, if you have this instrument that has these pins, this is the serial communication device. So in today's video, we're going to talk about the serial communication device, and later we're going to talk about instruments that can send voltage or current signals or analog signals. So what is RS-232 serial communication device? A serial communication device is the process of sending data 1 bit at a time. 1 bit, like 0, and then another 0, and then another 1. This is a byte, and each one of them is called a bit. So a serial communication device is the process of sending data 1 bit at a time, sequentially over a communication channel like a modem. So for example, if you have a sender, and then if you have a receiver, a sender is sending signals 1 bit at a time to the receiver. In contrast, the parallel communication sends several bits as a whole, and that is called a parallel. Like you have sending several bits at a time, whereas in the serial communication device you send just 1 bit at a time. So if first 0 passed, then another 0, and then 1, and then 1, and then 0. However, in the parallel communication device, you send 4 0 1, and then another 4 0, and then 4 1. So this is called parallel. And RS-232, which is basically those pins that I just showed you on your instrument, is a specific serial protocol that defines a wiring and flow control which is used to send these data bits. Originally, it was defined to use data between computers using modem and a telephone line. So that is like old computers, they all have RS-232 pins, and that is how you connected them to modem, and then you connect to the internet. I think you all might have remembered that in old days. This is how we connected to the internet. So if you have an instrument in your lab that has this kind of pins showing on the back of them, either a 25 pin or a 9 pin, this is an RS-232 serial communication device. And this video is going to show you how to communicate between that instrument and LabView. which is LabView is basically a software in your computer. So basically between this instrument and your computer. So assume that we have two pieces of equipment, like your computer and your instrument that is sending signals and reading signals, that they want to communicate with each other. So we have a sender and then we have a receiver. Data is generated by the sender and it is put inside the sender's buffer, which temporarily holds the data. So the sender generates the data, this data bits, and then there's a buffer in the sender that is going to hold the data. Then we need to have a wire to send the data from the sender's buffer to the receiver's buffer. So a receiver also has a buffer. This is called a transmit data or TX wire. So you need a wire that sends the signal from the sender to the receiver. You also need another wire on the receiver side, which is called an RX wire, to have this, this entire line connected. So now we have a cable that transmits the data and then the receiver that receives it. Once they are connected, once these two cables are connected, the data can flow from the sender to the receiver side. So we need to have a TX and an RX cable. What I'm telling you right now is basically all those pins that are on the back of your instrument, like what each one of those pins actually mean. So one of them is the TX and the RX. But this is not this simple. What if the receiver is missing? Then the sender sends the data and they are lost as they move. So if there is no receiver and the sender keeps sending data and there's only a TX, the data comes and then they just disappear because there is no receiver to receive those data. There is no wire. So the RS-232 designers, they added a control wire which tells the sender that the receiver is there. This wire is called the data terminal ready or DTR wire. So we have another wire which is basically a control to make sure that there is a receiver to receive the data. So if this wire is not connected, then you might lose your data. But if this wire is connected, then there is a set of control that makes sure that you receive the data. So, but there's always one cable on the sender side and one cable on the receiver side. And so the DTR or data terminal ready is for the sender side, and on the receiver side, this is called data set ready or DSR wire. So we need TX and RX wire to send the data. We need the DTR and DSR wire to make sure that the receiver is there to get the data. So this is like a control. When these two are connected, a proper voltage is set by the receiver. The sender knows the receiver is there, and once again, data can safely flow. So when these two are connected, there is a voltage on the receiver side, and the sender can read that voltage and make sure, okay, so we have the receiver, so now let's send the data, and then data will flow. There is also another thing. What if the sender transmits the data too fast? What if like sender is generating the data and it's sitting on its buffer side and it's transferring to the buffer side of the receiver, but the receiver buffer size is not that big, so it just can't hold it, and then every once in a while some data is lost. Actually, this is the speed, not the span. The speed this data is sent is called the baud rate. So this is the speed. If the baud rate is so high that the receiver cannot get this data out of its buffer fast enough, the buffer overflows and once again data is lost. To conquer this effect, the designer added another control wire so the sender and the receiver can coordinate when they send and receive the data. On the sender side, this is called the request to send or RTS wire. On the receiver side, this is called the clear to send or CTS wire. So just keep in mind the baud rate because the baud rate is important. So baud rate is the speed that this data is sent. And each instrument has its own specific baud rate that we have to have it in our LabView when we are making our program. So it knows that, okay, this is the baud rate of this instrument. So with this additional line of RTS and CTS, the receiver tells the sender when it needs to pause and buffer overruns are avoided. This is known as hardware flow control. The RTS CTS is a hardware that controls when data flows between the devices. So if your instrument can have all these wires connected, then you can bring the amount and the chance of the error that you can receive as low as possible. So make sure when you're connecting your instrument to your computer that all these pins are connected. This is easily be connected with an RS-232 cable, which already has all the pins and everything. But the instrument who has all these pins on and active is basically the better instrument. That means that it is considering all the possible errors that can happen. There's also some other wires that is called a data carrier detect or DCE, which tells the modem when the analog signal is being received from another modem, and the ring indicator, which tells the modem that the phone is ringing. But we mostly don't have modem, and that is not a problem. So we mostly have a null modem or no modem. So this is for like a really old instruments. So whatever I told you about like these wires was just, for you to have some information of like what is happening with this RS-232 cable. Let me show you this. This is the RS-232 cable. It can be a DB9 cable, meaning that it has 9 pins, or it can be a DB25 cables. That means that it has 25 pins. But no matter if it's 9 pins or 25 pins, or this RX, TX, DSR, DTR, RTS, CTS, DCD, or RI are there. So for example, for a 9-pin cable, you can see that pin number 1 is the DCD. No matter if this is like discharge or discharge, they are both DCD. So this is like a universal pattern. And for example, pin 6 is DSR. That is the pin 6, which is the DSR, and here the pin 6 is DSR. So if you Google DB9 cable map, no matter where you get and find it, they are all the same. So when you purchase a RS-232 cable, which has like 9 pins here and 9 pins there, you can connect the two instruments to each other if they are both 9 pins. But if one of them is the 25 pins and the other is 9 pins and vice versa, you have to get a proper cable, or you have to do the wiring yourself. You have to make sure that you connect the TX to RX, and for example, the DTR to DSR, the RTS to CTS, and all these things. And this is the map. So this is how I just want to give you some information, like what all these pins mean. You don't really need to know exactly what is happening and how the data are flowing and all these things, but that is not my job to teach you, and it's not 100% necessary for you to know. It's just that I want you to know when you're connecting a computer to an instrument with this RS-232 cable, what is happening and what does each one of these pin actually mean. So most computers and many instruments have built-in serial ports. Since serial communication uses the built-in serial port in your computer, you can send and receive data without buying any special hardware. However, modern computers without serial ports may require a USB to serial converters to allow compatibility with RS-232 serial device. So let me open a page. Yes, here. So for example, the computer that I have in the lab doesn't have an RS-232 pin, the DB9 or DB25 pins that I can use to connect to the instrument, because they might be used for other things, like for my monitor. So I have to purchase a hardware, which this hardware transforms my USB port in the back of my computer into a single asynchronous serial port for communication with RS-232 device. So the one that I purchased has 4 RS-232. It basically has a USB connected to a 4 RS-232 device, because I have 3 pumps and a weighing scale that they all do the communication with the serial communication. So I needed all these ports to be connected to my computer, and I don't have a 4 DB9 ports in my computer, so I purchased one of these that it can transfer USB communication, which is also kind of a serial communication, to the RS-232 for me, and for 4 ports. So you need these kind of instruments if you have a lot of instruments that is in your system, or if your computer doesn't have an RS-232 port. So this is one thing that I want to show you. So that's why I purchased that, because I needed that, because I have 4 instruments that they do the serial communication interface, and I needed that. Okay, next. Oh, okay, I had it here. Sorry. So yeah, this is what I was telling you. I talked about asynchronous serial communication, and I'm going to tell you like what is this. This is a form of serial communication in which the communicating endpoints interface are not continuously synchronized by a common clock signal. Instead of a common synchronization signal, the data stream contains synchronization information in form of a start and a stop signals before and after each unit of transmission. The start signal prepares the receiver for arrival of data, and the stop signal resets its state to enable triggering of a new sequence. So basically it's just like a luxury thing that is added to the serial communication to say that, okay, this is now the time that you have to receive the signal. This is now the time that the signal is a stop. And again, another stop and start, and then another stop. So in this diagram, this is what you see: a start, and then some data bits, and then a stop. And the RS-232 is one of the common kind of this start and stop transmission thing. Okay. Remember I told you that the baud rate is important, and the baud rate is the speed at that these data bits are sending from the sender to the receiver. This is important because this is the property of your instrument. And when you purchase an instrument, the manufacturer is going to tell you, okay, this is the baud rate. So you have to know the baud rate, and then you have to define it in your LabView program. There are also some other things that the LabView program needs to know from the instrument, and that is called a parity. So what is a parity? Parity is a concept to detect errors. It is used to detect a single bit error. So let's get started on. So assume that we have a sender, and our sender is sending an 8-bit signal to a receiver. There might be some noise sometimes that change the signals, in a way that some bits are changed from 0 to 1 or from 1 to 0. So you are sending the signals, the sender knows the signal, the 8-bit signals that has like a 0 and 1 in them. But then throughout its transfer from the sender to the receiver, something happened, and then you will have a noise. A parity is a way to detect that noise and tell you that, okay, we are having this error and this is the noise. This is like the way that we can, this is the way that the parity actually works. Parity is basically an extra bit that we send with a bit stream. There are 2 types of parity, an even and an odd. I'll explain this with an example. So as I said, assume that we have an 8-bit signal consisting of a 0 and 1. So I'm having an 8-bit signal consisting of 0 and 1. Assume that we are going with an even parity mode or type. So here our original signal is actually having like 3 ones, and actually a parity is associated with a 1. So it basically counts the signals that has number 1 in them. Basically it counts number of signals that is 1. So here our original signal has 3 1s. And if we go with an even parity, it means that we are going to add another bit to these signals and make it a 9-bit signal. And we have to, based on the even parity, we have to have even number of 1 bits. So if we have 3 1s here from the original signal, the parity bit is going to be 1. So this way we're going to have 4 1s, and that means that we are in an even parity type. On the other hand, if we are sending this signal and we are having 2 1, then the parity bit is going to be 0 because we are working with an even type parity. We should eventually have even numbers of 1. So that's why we are having 1 here and then 0 here. In the odd parity type or mode, it's vice versa. That means that we need to eventually have odd numbers of bit number 1. So if we are having 3 bit number 1, then in the odd parity mode, the parity bit is going to be 0. On the other hand, if we have 2 number of 1 bit, the parity bit is going to be 1 to keep up with the odd parity mode. So how is this parity is going to help us? Assume that we are having this original signal 0 1 0 1 0 0 1 0, and throughout it, and the parity bit is 1, of course, because we are going with the even parity. And throughout its transfer, a noise happens, and then that 1 is going to be switched by 0. So when the receiver reads it, it reads it at 0 1 0 1 0 0 0 1 and a 1. And it knows that it's an even parity, so it's going to count the number of 1s, and it sees that this is 3 1s, or it's an odd number of 1s. But this is an even parity. It should have been an even number of 1s. So then a receiver knows that this was a noise or an error. So this is how a parity is going to help us. So when you purchase an instrument, in the instruments manual, you will see the baud rate and you will see the parity, which is even or odd. And then you have to define it in your LabView program. There's also another thing that is called a flow control. I have explained you the flow control in previous slides, but I'm going to tell you again what it is. So basically, in many circumstances, a transmitter might be able to send data faster than the receiver is able to receive. Remember the baud rate? To cope with this, serial lines often incorporate a handshaking method, usually distinguished between hardware and software handshaking. So the hardware handshaking is done with some extra wires that I taught you, the RTS, CTS, or the DTR, DSR signal circuits. So if you remember, they were here. Like, remember, I was talking to you about this. So these are basically a way to control the flow movement. There is also no handshaking if there is no control, and in that, if you see a problem, this problem can be prevented by reducing the speed of the connection so that the receiver can always keep up, or increasing the size of the buffers. So this is called flow control. So now I'm gonna go to the lab, and I'm actually gonna record my instruments, and I'm gonna show you how these things are connected, and then I'll be back and we can open LabView.
Hey, so this is my instruments, and you can see that I have this USB to RS-232 converter, that one of these, actually this here, is connected to the back of my computer. So it's connected with this, this line to the back of my computer with the USB. So I have this connection with this box, and here I have 4 RS-232 port that is connected to these 3 pumps that I have here, and to the measuring scale that I have also here, because these are the kind of instruments that they have these kind of ports on the back of them. So this is how the serial communication transfer. It basically make a connection to the pumps, and then for example here I want to run the pump, so I have to send a signal from my computer to the box and then to the pump. So the pump will then operate based on a signal that I send to it. So for example, if I say run at 25 RPM, the pump will know how to run. And if I tell the pump to stop, the pump will stop. The fact that how the pump reads the command or the order is basically, again, something that the instruments will give you in its manual. For example, the manual of this instrument said that if you type H, that means halt a pump. So you basically have to look at the manual of your instrument or call the company that you purchased the instrument, and then you will know how to define the command based on a certain language that the serial communication works.
So this is the manual of my pump, the pump that I have in the lab, and you can see in the manual it's written that the serial data format that I have is that this serial data format is full duplex, simultaneously transmit and receive the data. It starts with like there's like a 1 start bit, 7 data bits, 1 odd parity bit, and 1 stop bit at 4,800 bits per second. So basically now I know that my baud rate is 4,800 bits, my parity is odd, I have 7 data bits, and I have a stop bit. So this is exactly what the instrument manual tells you. And if you like scroll down in your instrument manual, you will see how to define this code. So there's basically actually a format which is called, or a language which is called an ASCII table. So for example, a start of a text or SDX is basically 0, 2 in the hex language. So you just have to, read your instrument manual and understand how to define the code for your instrument. For example, for this instrument, it says that start it and then give your instrument a number or a name, which is PO1. In the video that I uploaded from my setup, you can see that the pump is written PO1 in it. That means that it's been connected to the LabView, and I have called it a PO1. And then if I scroll it down, you will see like there is all the commands that comes with the instrument. For example, H means halt or stop the pump. S means set motor direction and RPM. And G means go turn pump on and auxiliary output if present. And then R means enable remote operation. And ENQ or inquire means that basically it's inquire which satellite has activated its RTS line, and satellite here means the pump. So you just basically have to understand your instrument and the language of it. I'm telling you it's not that easy, but once you get it, it will be easy. But you can always call the company and ask for the commands and how you send the commands. They always respond. And you can also look at the manual if you want to figure it out yourself. So in the next video, I'm going to open LabView, and then I'm going to show you how we can communicate with the instrument using LabView.